Thank you. Hello. So yeah, I'm going to talk about parallelism. So to start with, we all know what concurrency is, but it's not exactly the same as parallelism. So concurrency is the running multiple goroutines at the same time, for example. And parallelism is, well, concurrency is running multiple goroutines, and parallelism is actually running them at the same time. So you can have concurrency without parallelism. And in fact, until Go 1.5, Go defaulted to just using one core. So it's not actually from the beginning that Go could use all cores on the system. On TinyGo, we used to use just one core of the system because, like, almost all microcontrollers have just one core. So why would you add the complexity of adding multiple support for multiple cores? However, things have changed a little since starting TinyGo. So one of the big changes is that there's now a very well-known chip in the maker scene, the RP2040 from the Raspberry Pi Foundation. And it has dual core, which is uncommon for a microcontroller, but it's very popular and we want to support it. Another reason to add support for concurrency in TinyGo is, for example, people have been using TinyGo on Linux, for example, the Euro project. And also, on WebAssembly, there's something I want to try. Right now, we use a Syncify to run multiple goroutines. However, using a Syncify is kind of a pain. So I would like to investigate whether using web workers in browsers, for example, works better. At first, I will focus on Linux support. And the reason is that's where I started. And in TinyGo, we are using one thread per goroutine, one operating system thread. And this is different from the main Go implementation. In main Go implementation, there are there are a few operating system threads, and a lot of different goroutines are scheduled on them. This gives very high performance, especially for things like HTTP servers, because you avoid a lot of overhead. But in TinyGo, it's more important to simplify things. So I decided to use one goroutine per thread. This means that there's no need for special stack switching when doing a CGO call or system calls. Can just make directly like read and write without like calling back into this scheduler and waiting using epoll and stuff like that. And we don't need to worry about for example, the main Go implementation needs to have checkpoints where it needs to check whether a goroutine needs pause. Otherwise, other goroutines might just be stuck waiting for one to pause for garbage collection, for example. And using operating system threads makes this all a lot easier. This uses a little bit more RAM and a little bit more context switching overhead, but that's like the priorities for TinyGo are different. Like we care mostly about like simplicity. So what needs to change? There's quite a few things that needed changing in TinyGo to make it support multiple goroutines running at the same time. Obviously, the scheduler. It was single-threaded before, and afterwards, like you have multiple threads, so you don't really have a scheduler anymore. It's the operating system. Garbage collection needs to be updated because it needs to stop the world. Gen and select statements in the Go language need to be updated. Package sync needs to be updated. Interestingly, sync atomic doesn't need updating at all, because we use LLVM built-ins, which are lowered to just native instructions on CPU cores. So that just works. And there are a few other things like println. If you have multiple coroutines printing at the same time, but and there's no locking involved, they can just interleave lines and just makes a mess. So there's just a little bit of locking around there. To implement all these new synchronization primitives, we're going to use futexes. Futexes are a Linux system call, and so what's a futex? It stands for fast user space mutex. That's not exactly what it is. You can make a fast user space mutex out of it, but it's a system call. And it's basically a building block for synchronization primitives. So things like wait group and stuff like that. The API looks something like this. This is just pseudocode, but this is what the operating system implements. It's based on atomic variables. And basically, there's one side that can call wait, and the other thread that can call wake. And it will wake up a waiting thread. Importantly, it doesn't. If the atomic variable changes, nothing gets woken up. You really need to make a system call. That's a common misconception. This API looks different across operating systems. On Linux, there's one system call that does a lot of different things for like super specific use case and optimizing things and stuff like that. On macOS, there are two private APIs you can use. They're private, so no guarantees, but they're also used in the LLVM C++ standard library, so I hope that's fine. And on Windows, there are a few system calls with very descriptive names, and WebAssembly also has some from the threading proposal that doesn't actually implement threads. That's basically a subset of all of the above. To make this simple in TinyGo, I made a wrapper type called a futex, and basically it adds a few methods on top of a atomic variable, because futexes are based on atomic variables. It's the wait call, the wake call, and waking all waiting threads. And of course, the same API also works on bare metal. However, in the case of bare metal, the TinyGo runtime is basically the operating system. So there's nothing to call to. So the futex type itself contains a linked list of goroutines that are waiting, and wait just adds to the list, and wake removes from the list. So that's fairly easy. And it uses a spin lock to make sure it's atomic. To give an example of how this is used, sync.waitGroup is actually one of the simplest concurrency primitives in Go. Internally, it's basically a counter. Like you can count up and down, and once it reaches 0, all the waiting goroutines will continue. So that's what you can see in the add call. It adds a number, and once it reaches 0, the adding number can also mean decrementing it if you add a negative number. But if once it reaches 0, it wakes up all the waiting goroutines. The wait method is a little bit more interesting. It basically waits until the counter reaches 0, but there are two interesting parts. One is there's a for loop, and there are two reasons for that. One is that the wait system call, futex system call, can actually sometimes return even when it's not woken up. Linux just does that. It's what the documentation says, so you have to work with it. So basically, once you wake up, you need to check whether it's actually woken up. And this is not important for wait group, but there is a possibility that between loading the counter and doing the wait, the counter actually changed. And if so, we need to check again. This is important in mutexes, for example. So yeah, that's why it needs a loop. Channels are surprisingly a lot simpler. I did, in fact, need to I did refactor the whole channel implementation in TinyGo for this purpose, but that was sort of needed for the rest. But just adding parallelism support just meant adding in lock, and if you need, and that's it basically. Any operation on the channel struct just meant taking the lock, doing the operation, releasing the lock. So that's simple. Select is a lot more complicated though. In this case, you can have so basically, if you have two goroutines that are doing a select on the same channels, you can end up in a deadlock. So for example, one goroutine waits for channel 1, the other way. So how select works is one by one, it locks all the channels in the cases, and once all of them are locked, it checks whether one of them can proceed. This is, I think, in fact, specified by the language, but I'm not sure about that. But what if the one goroutine locks channel 1 and the other one locks channel 2, and then the first one tries to lock channel 2, and then the second goroutine tries to lock channel 1? Well, that's going to end up in a deadlock, and we don't want that. The main Go runtime solves this by basically sorting all of the goroutines in the select statement before locking them. And if they're sorted, they're always locked in the same order, which prevents the deadlock. This is kind of complicated, though. So in TinyGo, I decided to go for a much simpler option. Whenever there's a select and it needs to lock all the channels, it first takes a global select lock. Not perfect, but it's simple and it works. So that is TinyGo. That's TinyGo support on Linux. And next up is a multicore support on bare metal, like microcontrollers. What I did first is run everything in QEMU. So we have a RISC-V QEMU target, and it can actually run the vast majority of standard library tests. So that's like a lot of code coverage, and if it works there, like we're good. This RISC-V target, RISC-V QEMU target is virt.io. So people with working on VMs probably know about it. So first, I basically added support for this system, and so we're running for every core in the system. There's one instance of the scheduler, and all of them are sort of working together. But it's a new. It's similar to the existing scheduler we used for single core operation, but for multi-core support. For garbage collection, we basically just interrupt all the other cores and let it wait until the stop the world phase is finished. And this is done using a software interrupt. And for time.sleep, one core uses the clock to sleep, and all the other ones are just waiting until there's a goroutine to run. So that's all in software, and that's all in emulation. That's not super useful. So next up, I added support for the RP2040 from the Raspberry Pi Foundation. And that's actually something I can show. So this is the Gopher badge. I'm not sure how much of this is visible, but yeah, you can. This is the Mandelbrot fractal. And here, when I added support for it, I added support for parallelism, I could definitely see a lot of improvement. So basically, Mandelbrot fractals you can see here are, oh wait, it's supposed to move, but it isn't. Anyway, it's supposed to be moving. So calculating the fractal is quite computationally expensive. So that's why it takes a while to render the whole screen when you move around. So one solution is parallelizing it across the both cores. And once I did it, I definitely got quite a speed up, which proves that multicore support is actually working and not just like working in tests. So that's like most of the. So now most of it is implemented. Some things I want to work on next is macOS support. It's almost done, but just need to fix a test somewhere. There's just one issue that on macOS, I think you can only run up to 2,000 threads or something. There's some limitation that doesn't apply to Linux, so it might not be great to use one thread per coroutine, but we'll see. I will want to investigate WebAssembly support. Not sure how useful that will be, but will be interesting to see. Maybe I'll work on ESP32 support, but for those that don't know, the ESP32 is a Wi-Fi chip, a very cheap one, and it is dual core, one of the first cheap dual core chips. But currently we do not have Wi-Fi support on it, so like that's the whole point of the chip. So it's not super useful in TinyGo so far. But maybe we'll get to it. And of course, there are performance improvements we can make. But first, we had to implement basic support. So that's it. Actually, I can recommend something. Maybe a bit dangerous to mention here, but this is a very good book about concurrency. But seriously, it's a very good book. Just ignore the rest parts, basically. But it's very accessible. Anyway, that's it. So here's the slides if you want to see them.